Okay, everyone, so we're back and we are looking at a presentation on capacitors today. And as we go through this presentation, you'll see it's basically going through the same kind of objectives that we did when we looked at inductors, and how an inductor is just a coil of wire, and how a capacitor is actually just two electrically isolated plates, where the plates are so close together that the electrostatic field, that is the forces of unlike charges, as in plus and minus charges in electrical, or north and south pole charges, if you think of a magnetic field for an inductor, how there's an attraction of opposite charges and a repulsion of similar charges. So like charges repel, opposites attract. So because of this, this attraction of plus and minus charges is called an electrostatic field. So we'll be following through in the same way we did for inductors, looking at what makes up a capacitor, what are the different variables that affect a capacitor's value, the unit that represents capacitance, and then looking at capacitors and inductors in series and in parallel and so on. So that's kind of the same thing we're going to be going through today. So again, a capacitor is two electrically isolated plates, and we have the schematic symbol shown here for a capacitor. And just like it shows, it kind of looks a lot like a DC source or a battery with two plates of equal size. And really, you could think of it in a lot way like a battery, with because it stores voltage and stores energy, and that energy can be used to deliver energy for a very short period of time back to a circuit, or in an AC circuit, it continually consumes and returns energy to a total net real power value of 0. It doesn't do any real work, just like an inductor. So when we look at the capacitor, again, we have our schematic symbol here, and instead of a magnetic field like there is with an inductor, we have an electrostatic field. So inductor was a magnetic field. For a capacitor, it's an electrostatic field. So when we have a charged capacitor, we have one plate negative, one plate positive. It's storing that that energy or that voltage such that it could act like a source for a momentary current discharge in a circuit. So when it comes to capacitors, what we're going to find is that a capacitor is almost like, you could say, always opposite to an inductor. So if we take as an example what we've learned for inductive reactance, XL. XL, we know, has a direct relationship with frequency, so XL equals omega L, or 2 pi FL. And so we have a direct relationship with capacitance, which is XC. We will see that we have a 1 over omega C value, which is 1 over 2 pi FC. Now notice how there's an inverse relationship with frequency here. The higher the frequency, the lower the reactance. So notice how we're already seeing the essentially the opposites being applied from XL to XC, from inductor to capacitor. In the same way too, as we're looking at a capacitor and its voltage current relationship, remember, for an inductor we had the acronym ELI, right? That meant that current lagged the applied voltage. So if we were to use voltage as the reference, current is lagging. I think you can imagine if you were to now say, well, if we're learning that capacitance is the opposite, what would that mean? That would mean for capacitance, we have this acronym. And so if we're looking at voltage as the reference again, we can see that current leads. So I leads E, and over here, I lags E. Notice how we have that opposite. Okay? So when we're talking about capacitors, we're talking about two electrically isolated plates and the electrostatic field. when we said an inductor, L, opposes changes in current. And that's when we used an inductor for surge suppression in power systems. We have C as our capacitor opposes changes in voltage. So I'm sure if you guys get to it in your 232 course, you'll look at DC power supplies, and part of a component in a DC power supply is something called the filter that filters out the ripple from the output of a rectifier. And the component that's used to filter out those voltage changes is a component that opposes changes in voltage. And that would be a capacitor. And that's how come you have capacitive filtering in power supplies. If you were to open up some power supplies in the lab and look under the hood, so to speak, you would find capacitors of varying sizes in there that are used to filter the output from the rectifier in that power supply. So that's what we're talking about today, is capacitors. So this is chapter 10 of your Robinson Miller book. When we look at capacitance, it's defined as the ability of a dielectric or the insulator to store an electric charge. It's also the measure of how much charge can be stored. So we said they're electrically isolated plates. Now, between the two plates of a capacitor, you could have simply an air gap. That air gap means that what's called the dielectric, the material between those two plates, would be the dielectric constant, or the dielectric value of air. And there is such a thing as just simple air gap capacitors, but a lot of times there's special materials that'll help increase that capacitance value. So we'll learn about a few of those, but it's called the dielectric material between the two plates. So if we were to look at a capacitor and the two plates, whatever is in between here, in between the two plates, is called the dielectric. And again, it could just be air, or it could be a special material. So capacitors are components that are used to store charge. The abbreviation for capacitance is C, and the unit now, it's not henries or ohms, but it's farad. Now, once we convert a capacitor to its value of reactance in an AC circuit, where we're determining its opposition based on omega, or angular velocity, well, then of course we're going to be looking at its value in ohms. But when we're just looking at its value as its measurement of storing charge, and the unit that indicates its measurement of storing charge, we're talking about a farad. So that's where you're going to have things like microfarads, millifarads, and whole units of farads. Okay. Now notice how it says capacitors resist a change in voltage. So we just generally say that inductors oppose changes in current and capacitors oppose changes in voltage. And again, we said that capacitors are used in input-output circuitry of power supplies. So that if you have the rectifier output, like you would from a full wave rectifier, looks like this, with 0 volts here and some DC value of voltage maxing out for these peaks. What's the job of the capacitor? Well, you bring in a capacitor that resists these big changes or delta voltage values, and you can smooth it out. And the more capacitance you have, the more you can smooth this out to give you a near perfect DC voltage, right? So that's the idea. It takes large fluctuations and turns it into a nice, flat, steady DC value. So one thing to remember about capacitors is they have, a practical capacitor has a maximum working voltage. So I think, as you can imagine, if the force is high enough, we know that we can get, we can bridge two conductors with an arc. So if we have a high enough voltage, if we have a high enough voltage here, if the voltage is high enough, this dielectric that separates this two plate will break down, and it'll no longer be an electrical insulator. It'll allow it to conduct, and then you'll end up with a shorted capacitor, shorted cap. And there should never be electrical current flowing between the two plates, right? There should never be electrical current. But if we know, just like in lightning strikes and so on, if the force is high enough, you can break down any insulator and it will conduct. And it's the same idea with a capacitor, and that's what gives a capacitor a maximum working voltage. Okay, so it's something to be aware of whenever you're working with them. So this is essentially looking at what we talked about as our electrostatic field of our capacitor, where if connected to a source and through a resistance, right? So here we have current flow. And notice how when it comes to something called capacitor current, capacitor current, there actually isn't a closed loop, because remember, this is an open, right? So the capacitor is two electrically isolated plates. So because they're isolated, that means that we have an open. So can you have current flow in an open circuit? No, but when the plates are close enough such that it allows an electrostatic field to build, during the time that the electrostatic field is building, you will have current. Okay, but once this capacitor is fully charged, we have no current. So notice how here in this statement it says capacitor charged to a value of V source. So that means at that point in time, the value of VC is going to equal Vs, and now we have a charged capacitor and there is no more current flow in the circuit. We've reached our steady state condition of I equals 0. Okay, so now we have a charged capacitor, and when we have a discharged circuit, that capacitor could discharge into a resistance. Charged capacitor. Okay. So when it comes to schematic symbols, we have several here. Notice how we have the typical variable capacitor on the end here with the arrow pointing through the schematic symbol. This is what's called a non-polarized capacitor in the middle. That means it doesn't matter where you connect a positive charge and a negative charge. When it comes to electrolytic capacitor, notice how that's a polarized capacitor. It marks one side positive and the other side negative. I think it would be logical, and you'd be right to say that if that's the case, these electrolytic capacitors are only used in DC circuits. And just a little bit of a story there. Electrolytic capacitors are used to do that filtering I talked about in that power supply. And if you are building that power supply and you connect the electrolytic capacitor onto the AC side of the rectifier instead of the DC side, it explodes. And back in the days where we used to do a lot of those labs and building those power supplies, we used to see them blow regularly, and they would just literally explode, and it would be as a result of connecting an electrolytic capacitor on an AC side. So you never want to connect an electrolytic to AC. Okay, so this is how we see a capacitor constructed. And notice how we have that dielectric material I talked about in the center, and then essentially two electrically isolated conductive plates, and the schematic symbol being over here. And of course we know that this value for this capacitor would be in farads. Okay. So capacitors are designed in all sorts of ways in order to essentially give you more capacitor plates in a smaller area. So notice that how that's been done here. It's basically a sandwich type layering of the plates and a dielectric material like what we see here. This would be a mica dielectric, right? And then you'd have one plate which could be at one point in time positive and the other point negative. And now you've got two positive plates, two negative plates, that as a result it's giving you more plate area and more capacitance by this design. And this is basically a wafer or layer type mica capacitor. So ceramic disc, no real difference other than you have two coin-like discs separated by, once again, a dielectric, and the ceramic is really speaking to what's in between the two plates, and in this case you can see it's a ceramic material. Okay, then there's the axial capacitor, or the jelly roll type capacitor, where we just roll this all up to give us a large plate area, and with the two plates being separated by a dielectric again. All right, so that's where we find the dielectric in the jelly roll style. Now, when it comes to electrolytic capacitors, like I was talking about, they're generally built like this. So when they blew up in the lab years back, when I was telling you about that, you would actually see all these layers in an exploded view, basically, literally an exploded view, and all the stuffing and the dielectric and everything would all like explode out of it. But I think you kind of get the idea. The idea is that giving you more plate area is significant here. More plate area is actually going to give us equals more F, more farads, more capacitance. So yeah, just some talk about capacitors there. Not, you can review that. It's not really specific to what we're to what's important to our studies, but again, you know, review that. Here's where we get to something that matters, and you know that when we talked about resistors, we had our rho L over A to determine the resistance of a conductor. When we had the inductor, we had our mu value multiplied by our number of turns squared, multiplied by the area of the coil, and then divided by its the core length. Well, this is really what we're talking about here when it comes to the capacitance of a plate capacitor. So it means that when we look at everything involved here, of course, C is our value, our total value of capacitance, and that'll be a value in farads. So don't forget C is in farads. And so when we look at this variable here, this is our dielectric constant. So this is a table that you would find listing dielectric constant values. There'll be one for air, one for mica, one for ceramic, and plastic, and all the different types of dielectric materials they use have a dielectric constant, and that's what's used in this equation, is that value. And if you look in your textbook or go online for dielectric constants, you'll find a table that gives values for different types of dielectric material. Now, notice how here we have a direct relationship with the plate area. So just like I was saying, more plate area is going to give you more capacitance, or more of a value of farad. So that's where area comes in. Now, if we look down here though, we have an inverse relationship with the distance between the plates. So that's simply saying that if we have plates more separated, they're not going to be able to develop that electrostatic charge like if they're infinitely close. So as a result, what we end up with is an inverse relationship there. So what does that mean? What is the most practical way of providing a variable capacitor? Well, that's by shifting the plates. So mechanically shifting the plates is going to essentially affect the plate area. Now, notice how obviously when it comes to these plates, they're still the same size plates, but they've been shifted so that essentially the overlapping of the plates, which would be the part that develops capacitance, has been affected by the shifting, right? So notice how there's less capacitance because essentially the plate mesh is less. So this is the most practical way of creating a variable capacitor. So this is just a quick picture of an example of a variable capacitor. This would be like in a tuning circuit, so a radio tuning circuit, a television tuning circuit, or something of that nature. And what it means is you can rotate this knob here at the end, either this shaft, either clockwise or counterclockwise, and I think you can see by looking at it, when you do, you'd affect the plate mesh. So there's a bunch of half moon plates, and they could be meshed like this, right, with about 50% mesh, or you could continue to turn them and get one piled right up on top of the other to give you maximum plate mesh. But at the end of the day, we're just really demonstrating that this is giving you a visual idea of meshing plates and varying the amount of mesh or shifting it and creating a variable capacitor. If we look at how their relationship is affected by distance, you can see that here. The closer these plates are together, the higher capacitance value can be developed by that electrostatic field. But of course, the closer they are, then the easier it is to break down the dielectric and get shorted capacitor. So it is what it is, but we obviously have more capacitance, from a smaller distance, right? Because don't forget, if we look back at that equation, we have smaller distance, more capacitance, wider distance, less capacitance, and that's that inverse relationship with distance between the plates. So really, what are we talking about when we look at this? Well, we're looking at the same idea as what we talked about when we talked about conductors or inductors. We can just use it to have a better practical understanding of capacitors. As an example, what would happen if we doubled the plate area? Well, doubling the plate area would double the capacitance because we'd be putting a 2 times value into this equation, right? So we'd be putting a 2 times value here. What would happen if we did a 2 times value on the distance between the plates? 2 times value on the distance between the plates would mean, because of that inverse relationship, we would have a C value half of what it was. So you kind of get the idea there, is that's an example of where we just have an understanding of how the different variables affect the capacitance of that component. Okay, so going forward here then, what we're doing is we're taking a look at capacitors in series and in parallel and combination. And again, if you look at your formula sheet will have these formulas for these connections, and it will say right beside it, capacitor in series, capacitor in parallel. And notice how this is again where we have our opposites between inductors and capacitors. A parallel capacitor connection is now one that's found as summing the values together, right? So we just take the value of one in farads, add it to another in farads, add it to the third in farads, and that's going to give you the total. Now, you can look at your formula sheet, you can say to yourself it's the opposite of inductors, so I'll just remember it that way, whatever you decide. But one way that I look at this is I think about these 3 parallel capacitors, and in a lot of ways you could say, well, that in connecting them in parallel, what you've done is increase the plate area, right? You've increased the plate area such that every time you add another one, you've got more plate area, and we know that's going to result in more capacitance. So it's got to be an additive thing. So however you remember it, or whether you just consult your formula sheet or whatever, understand that parallel capacitances are simply added, or the sum of. So then it should be no surprise that if you look at the series connection is where we have the sum of those reciprocals, right? So that would be what you do for a parallel inductor, but the capacitor is the opposite. So for a series capacitor, it's the sum of the reciprocals. So what would that mean when you have a series parallel combination? Well, you can go through this and you can just confirm this answer and make sure this is correct. But what is simply the approach? Well, it would mean that these two capacitors on the end, because they're in series, would be a product over sum calculation, right? Once you come up with a product over sum calculation, then you can simply add it to C5, right? Now you've added it to C5 because capacitors and parallels just add together. Then product over sum with C4. I think you're getting the idea. Product over sum with C4. Then once you have that, that's going to be a value that's in parallel with C3. So you can do an adding of C3 to this C equivalent value. And once you have that, then you'll just use your sum of your reciprocals with that C equivalent. So essentially, you'd be working with an equivalent circuit that would have C1 in series with C equivalent in series with C2, and you're determining the C total value. Okay? So be aware and review that, and of course the exercise that I have for you will review that and have you make sure you know how to do that. Okay, so let's just take a look at capacitor voltage here, and this will be kind of where we can segue from this into capacitors in an AC circuit. So if we look here at a DC source connected to a capacitor through a resistor, it means that when we connect this source, the moment we connect it, this capacitor is going to charge. So we're going to have a period of time, not long, until this capacitor VC, this VC equals E source. Once it equals E source, the capacitor will be fully charged, okay? And I will be 0. There'll be no more current flow. Now, that means that when a capacitor reaches its steady state value, which is its charge value, that there's going to be the equivalent of the source voltage across it and no current through it. That's the steady state equivalent of what? Would that be an open or a short? Well, remember, source voltage and no current is an open. So we're talking about the steady state equivalent of a capacitor being an open. Okay? So here's where we see the voltage and the current. Now, this starts at time 0, right? So right here in our graph is where we have time 0. At time 0, this is the moment we've connected that source, as soon as we've connected that source. And down here, at the end of both, is where we have a charged capacitor. So if we look at both these, this is charged capacitor. Okay. Now, once the capacitor is charged, remember we have I equal to 0, like what we said in the previous slide, and VC equal to E source. So notice how here the red curve is indicating that the voltage has reached its maximum value when the capacitor is charged, a value of Vs, and I is equal to 0. But here's where we're going to pull something from this whole relationship. If we look at the moment the voltage is connected, right here, this is where the capacitor is showing its reactance. It's reacting to that change in voltage. It's opposing that change in voltage. It's accepting the change of current, you could say, but it's opposing the change in voltage. So what do we see? We see an immediate change in current going right up to an I max value. So that's an I max value. But we see right at the moment the source is connected, V is 0 volts and I is at a maximum. What happens when the capacitor reaches its steady state value? We have voltage at a maximum and a current at minimum. So we have I min here and we have V max. Really, what are we pulling from this? Well, we can see the current is the first to reach maximum and the voltage comes later. So that allows us to support what we said was the voltage-current relationship for a capacitor. Notice how current leads voltage. So current is leading voltage. I leads V. And that's what we see in this case, is we see current is the first to reach maximum right away as soon as that it exposes to that source, or the source is connected. And then over time, the voltage reaches its maximum value and the current reaches its minimum. That is really taking us to our initial understanding of a capacitor in an AC circuit, and where I leads V.